All right, in section 4, we're going to be talking about two topics. The first one is we're going to review the concept of symmetry, and then we're going to talk about classifying functions as either even or odd functions. Now, symmetry we've all heard of from geometry and other places. It's where essentially it's the same on both sides. So if I have a heart and I make the other half of the heart, then I have a symmetry because it's basically the same on both sides. There are two types of symmetry we'll really look at. One is called reflectional symmetry, and that's when a graph has symmetry when you can fold it over some line onto itself. For example, this heart. If I fold this heart in half over this line, it will go right onto itself. The other type of symmetry we see is what's called rotational symmetry. And rotational symmetry is when it can be rotated less than 360 degrees and look the exact same. So a lot of times you could talk about being 180 degrees. So I could talk about a mathematical graph that looks like this. So if I were to rotate this around the origin, rotate it around the middle, then it would look basically just like it does right now. It would just turn on itself. Some shapes have both rotational and reflectional symmetry, like a square. If you think of a square, I could fold it over this line and it'd be the same, or I could rotate it about its middle and it would be the same. Those are both types of symmetry. So if we look at some different functions and try to figure out if these have rotational or reflectional symmetry, pretty easy to tell which one is which. This first kind of wavy graph obviously has reflectional symmetry. And the reflectional symmetry is about the y-axis. Because if you flip it over the y-axis, it's the same on both sides. So if I flip that red back onto the blue, it would be the same. So the one to the right, this parabola, it also has reflectional symmetry. But it's not on the y-axis this time. This one is flipped over the x-axis. All right, if we look at these two graphs down here, this one is very similar to the one I used as an example above. This one would have rotational symmetry because if you flip it 180 degrees about this point, it's going to be the same because this part here would become this part here. So this is rotational. And we would say about the origin because this is the point that you rotate around. It can really be any point in the plane. Origin is one we see a lot. Finally, this was a parabola. Now this one's a little harder to see the symmetry. It does have reflectional symmetry. And again, for all these, you could always graph it if you were just given an equation. But in this case, the line that would fold it in half is kind of this line, right? So that's not really the x-axis or the y-axis. This is the line 2. And it's the line x equal 2. Just remember, all vertical lines are always x equals some number. And all horizontal lines are always y equals some number. That'll be something that'll come up quite often in this course. All right, the other topic we're going to tackle in this section really is going to talk about even and odd functions. Now, when we talk about the formal definition of even and odd, it's going to sound pretty different, but it actually is related to rotational and reflectional symmetry, like we talked about before. So even and odd numbers, if you remember what an even number is, even numbers obviously are numbers that can be written in the form 2k. So 2 times any number will make an even number. And for an odd, 2k plus 1. 2 times any number plus 1 will always make an odd number. Now functions are a little different because there are even functions and there are odd functions, but then there are functions that are actually neither even or odd. So that's the one difference in functions versus numbers. So a function is considered even by definition if for all x, f of negative x equals f of x. So if we plug in negative x and get back the original function, you should get an even function. For an odd function, if we plug in negative x, f of negative x, we should get the opposite of the original function. And then if neither of those statements are true, then you don't have an even or an odd function. So really the big thing we're looking for in an even and odd function, we're trying to figure out what is f of negative x. Does the negative sign disappear, or does the negative sign make the whole function negative? So in this first example, we're going to try to figure out if these functions are even, odd, or neither. So the first function says f of x equals x squared plus 4. So really what I'm going to look for is what is f of negative x. So in function notation, when you have something inside the parentheses, that means you're going to replace it with what's in the parentheses for x. So f of negative x is going to be negative x squared plus 4. Now when you take a negative number and square it, negative x times negative x is simply positive x squared. So the negative sign disappears. So if you notice, we are back at the exact original function we started at. So because f of negative x went right back to the original function, this is an even function. Okay, let's look at another example. Now, if you look at this next one, f of x equal x cubed plus x plus 2, you see the exponent of 3, so, we started to maybe think maybe that's odd. But you have to be careful, because remember, some of them can also be neither even or odd. So what I'll do is I'm going to take f of negative x, so I'm going to replace all the x's with negative x, and in this case there's 2. So when I think of negative x cubed, negative x times negative x is positive x squared, but then when I multiply it by another negative, I'm going to get negative x cubed. Whenever you have 3 negatives, it's still negative. Whenever you have 2 negatives, it's positive. So we have plus and negative, so that's going to be minus x plus 2. So when you first glance at this, it looks like it's the opposite. It looks like it's the opposite of the original function. But this is actually not the opposite of f of x. And the reason is if I go up here and I look at f of x, if I was going to turn this entire function negative, it would be negative x cubed, and then negative x, but then it would also be negative 2. But if you notice, nothing really changed the sign of this functional value. The 2 is still the same. So this is not the opposite of f of x, and it's obviously not f of x. It's not the original, of course. So this is actually neither even or odd. And that's kind of the difference in function even and odds. It actually could be neither. So let's look at our last example. It says f of x equals 2x cubed minus 6x. Now, same idea. I will put in negative x for all the x's. So I have 2 times negative x cubed minus 6 times negative x. And the same idea, when you take negative x cubed, you're going to get negative x cubed outside the parentheses. So that's going to become negative 2x cubed. And then negative 6 and negative x is, of course, positive 6x, because 2 negatives are a positive. Now this is the exact opposite of the function, because I take the opposite of the 2x cubed, which is the negative 2x cubed, and the opposite of negative 6x, which is positive 6x. So because this is the opposite of the function, this is an odd function. So finding even and odd is not a terribly hard algebraic thing, but it is kind of tedious. So there is actually a way we can determine whether a function is even or odd actually using their graph. And it's what's called the even and odd symmetric theorem. So actually, this is actually a really easy theorem to know. So it says if a function is even, it will always have reflectional symmetry with the y-axis. So it'll be reflected over the y-axis. If a function's odd, it'll have rotational symmetry with the origin. So we're really trying to figure out if it's reflected over the y-axis or with the origin. Now if we look at our examples above, we can actually check that out. So if I look at the graph of the first one, recall it was x squared plus 4. We said that it was an even function when we did our algebra. Well, if I look at the graph of it, the graph of this, and you can graph this on Desmos or whatever you'd like, you can see it kind of looks something like this. Well, it definitely has reflectional symmetry about the y-axis, so that's why it was even. So even because it's reflected over the y-axis, or it has reflectional symmetry. So if I look at the second example we have, if we recall from above, it was f of x equals x cubed plus x plus 2. And if I graph this one, it looks something like this, and again, use Desmos. So this appears to have rotational symmetry about this point. But the problem is that point is not the origin. The only way you have an odd function is if it's symmetric or has a rotational symmetry with that point, not this point, which is 0, 2, I believe. So this is neither, because it's not symmetric to the y-axis and it's not symmetric to the origin. Now our final example, if you look at it, which was f of x equal 2x cubed minus 6x. If I graph this one on a graphing utility, I see something that looks like this. So now, obviously no reflectional symmetry about the y-axis, but if I look at this point in the middle, it definitely has rotational symmetry about the origin. Because if I rotate this 180 degrees, the graph would be about on itself. So since it's symmetric about the origin, that's why this is an odd function. And that's because it is symmetric or rotated about the origin. So these are both really efficient ways of finding whether a function is even and odd. And the real benefit of this, when we start analyzing functions in the future, we will always see if they're even or odd, and they will give us different properties of those functions.